Hello, my name is Adán Jair Serna Reyes from Universidad Tecnológica del Norte de Aguascalientes. My colleague is Dr. Jorge Eduardo Macías Díaz from Universidad Autónoma de Aguascalientes. And today we are going to talk about a convergent two-step method to solve a fractional generalization of the Rosenau-Kawahara system. My talk is divided in 4 parts. In the first one, I am going to talk about the origin of the Rosenau-Kawahara system and the fractional generalization of the derivative, the Riesz derivative. Then we are going to talk about the fractional generalization of the system and some properties. Following with the discretization of the model, the operators we will be working with, the properties that the method inherits from the continuous one, and the proof of existence of a solution. For the numerical properties, we are going to show some quick proofs for the consistency, stability, and convergence of the scheme. And finally, we are going to conclude with a summary of the talk and a small list of future work. Let's start with the background. It is important to point out that the main use of the Rosenau-Kawahara system is to study nonlinear waves. The nonlinear wave is one of the most important scientific research areas. Lately, many scientists develop different mathematical models to explain the phenomenon, such as KdV, RLW, the Rosenau equation, and many others. The first equation is the KdV, which stands for Korteweg and de Vries. Many studies have been done on the system, including solitary wave and traveling wave solutions and numerical simulations. The second equation is no other than the regularized long wave, a model for small amplitude long wave of water in a channel. But it fails to describe wave-wave and wave-wall interactions. For that, Rosenau proposed the so-called Rosenau equation, and properties like the existence and uniqueness of a solution for this equation have been proved. Conversely, to consider other behaviors of nonlinear waves, some viscous terms are included in the Rosenau equation, resulting in the Rosenau KdV and the Rosenau-Kawahara equations. The last one is alluded to Jin-Ming Su. It is convenient to define the tools that we are going to use. Our domain is omega, an open subset. Omega sub t is the Cartesian product of omega and the temporal interval. Next, we will be using LXQ, and it is natural to use the LQ norm and inner product. We let alpha in this subset, and U extends as 0. Here we have the definition of the Riesz fractional derivative. Note that we can decompose that integral into the left and right Riemann-Liouville fractional derivative. Moving on with the problem statement, it is important to point out that the main properties of the model are the conservation of mass and energy. Here we propose our generalization of the Rosenau-Kawahara equation, with U sub 0 a function that describes the initial conditions along with the constant beta. This is an initial boundary problem. The purpose of this generalization is to obtain a fractional correction of the nonlinear system, giving us a better understanding in dynamics of dense discrete systems. According with the non-fractional system, we propose energy and mass functions. A significant property from the Riesz fractional derivative is the existence of a square root operator, so we can rewrite the energy function as the last equation. Two important properties of the continuous model are that the energy and mass functions are conserved through time. By directly deriving each of the elements of the energy equation, we get the first two equations. Then it is useful to calculate 2 times the inner product of the function with the remaining elements of the partial differential equation. This is the first one. By hypothesis, in the boundary, the function is equal to 0. and the inner product as well. Keeping the same idea in mind, these are the remaining inner products. For the same reason, they are all equal to zero. The energy proof goes as follows. Since we have the left side of the differential equation, this inner product is equal to zero. From the previous identities, that is equal to 2 times the derivative of the energy, so the conclusion readily follows. The mass functional is also constant after some mathematical manipulation. In this section, we are going to propose a discrete implicit model, show the existence of a solution, prove the conservation of the discrete energy and mass, and a quick sketch of the proofs for stability and convergence. So we define a uniform partition for each interval. Next, we define the discrete time operators. We notice that the first corresponds to the average value and the second the derivative. Also, we need to consider discrete space operators. In order, they approximate the average value, first, second, third, and fifth derivative with a quadratic order of consistency. We are going to use fractional center differences for the discretization, defined as follows. This lemma helps us to approximate the fractional derivative, so it is instinctive to define the next discrete operator, which is going to work as the fractional derivative. Now we present our first discretization of the model, which has some interesting properties. First of all, we prove with the help of Brouwer's fixed point theorem the existence of a solution. It also has energy and mass functions, and those quantities are conserved in time. It has also a quadratic order of consistency, and finally, with a discrete version of Rönnbell's inequality, we proved that it is stable and quadratically convergent. These lemmas are going to be useful for the existence proof. As we expected, the discrete operator also has a square root. Finally, this is a version of Brouwer's fixed point theorem. We list the next identities because they are useful in the proofs of existence, conservation, stability, and convergence. The main idea is the use of the definition of the discrete operators. Most of these identities are equal to zero since the hypotheses of the system are homogeneous. The following theorem says that under any set of initial conditions, the numerical model is solvable if U is sufficiently smooth. That is done by induction. We consider that the previous n steps exist, and we are going to prove that the n+1 step also exists. The proof starts by defining a function g as follows. Then, we calculate this inner product, making use of the Cauchy-Schwarz inequality and some mathematical manipulations. We obtain this result. After that, we are able to consider energy and mass functions. Here we have the discrete version of the energy function, and the next theorem says that the discrete energy is also constant in time. Let's start the proof with this inner product, that it's clearly equal to zero. Then we may change the first element for the left part of the discrete equation. After using the previous identities, we obtain the discrete version of the energy derivative, and that is what we wanted to show. We also wrote some useful properties for the conservation of mass. We defined the discrete version of the mass function and its respective theorem of conservation. The proof is similar to the previous one. For the proof of consistency, we define this continuous functional and its discrete counterpart. This theorem says that if U is smooth enough, then the scheme is quadratically consistent. The proof makes use of Taylor's expansion for each of the elements of the discrete system and the triangular inequality. For the stability of our method, we use a discrete version of Rönnbell's inequality. Now, if we consider two solutions and the error sequence, these lemmas will facilitate the demonstrations of stability and convergence, especially item B, since that is a way to bound the nonlinear part of the system. It is easy to verify that the error sequence is also a solution of the discrete system, and the following theorem establishes the conditions for the stability of said system. Taking the inner product of the equation of the system with 2 times the average value of xi, next using some of the previous identities, we get this relation. Taking the sum over k and simplifying, we obtain the next bound for the n plus 1 step error and the derivative error. The proof ends by taking the n plus 1 term of the right side of the inequality to the other side. Gromwell's inequality is now satisfied. A useful corollary is obtained. The discrete problem is uniquely solvable. The proof is also straightforward, since the initial discrete solutions are equal to the exact solutions. Then the errors are equal to 0. And the previous inequality tells us that the norms of the m-step errors are equal to 0. So the functions are equal. The convergence proof is similar to the stability. Only in this case, we also take in consideration the local truncation errors. Then the following theorem states that if the system is uniquely solvable, then our model will converge to that solution. And we are almost done. We continue with the conclusions. In summary, we proposed a generalization of the Rosenau-Kawahara system, which describes nonlinear waves. We proved that both the energy and the mass are constant in time. Then we proposed a discretization of the system that inherits the properties we just mentioned. We provided a demonstration of the existence of a solution. Next, we proved the order of consistency of the method, stability, and convergence, also adding a computational simulation. I have to mention here that the simulations will be included in the extended paper, but we had a little rush to participate in the Congress. So that is the reason why we did not add them here, but they confirm the properties of the scheme. For future work, we want to try with more methods for the system, including non-conserving ones. Also try with different fractional derivatives, and finally apply these results to other systems. We are currently working on a few projects. Before we finish with this presentation, I'd like to talk about some of the references for this talk. The first reference is the only non-fractional discretization of the Rosenau-Kawahara system. From the second reference, we found the ideas for the invariants. Of course, we will not miss the definition of the fractional center differences, and finally an article in which we propose another generalization of a system, in that case the Gross-Pitayevsky equation. That system is conservative as well. In the case that you have any questions or suggestions, our information is at the beginning of the presentation. We will be more than happy in trying to answer them. Well, we hope you find this research interesting and useful. Thank you for your time.